Hello, everyone. We are going on to chapter 15 today. Chapter 15 is NMR. Let me go ahead and pull that open. There's a lot of concepts in here that are physics related or instrument related as far as like instrument manufacturing. So the more important details for you guys will be to know how to interpret the data. But they do go into a lot of theory that I don't know if is as necessary. Like I said, there's a lot of theory that they put in here, and I don't know how necessary all that theory is, because that's for the instrument manufacturers. So it says NMR spectroscopy may be the most powerful method of gaining structural about organic compounds. I don't know if I even agree with that. It is a powerful tool, but we do have mass spectrometry. Let me, as we talked about in our previous lecture, mass spectrometry, in my opinion, might even be, in my opinion, it's more powerful than NMR. There's a lot of older chemists out there that say NMR is the most powerful technique, and it is a powerful technique, but mass spectrometry has taken this over. NMR involves interaction between electromagnetic radiation and the nucleus of the atom. Basically, you're going to get some type of spectrum. You can have carbon spectrum. You can have a carbon spectrum would be carbon-13. You can have hydrogen. There's different spectrum out there. It doesn't just have to be hydrogen. They say they're going to focus on carbon and hydrogen, but sometimes you got to focus on other elements too. It says protons and neutrons in a nucleus behave as if they were spinning. If an odd atom has an odd number of protons and or a number of neutrons, it'll have a net nuclear spin. You can see right here, or an odd number of neutrons. So this has 7 neutrons, right? And there are, people do look at nitrogen and phosphorus NMR. The spinning charge in the nucleus creates a magnetic moment. So that's what we're trying to do. Trying to create this magnetic moment, as you can see. So when there's no magnetic field, you'll have a spin going in all different types of directions. When you apply that magnetic field, you're either going to go spin up or spin down. So the beta spin state is the opposing beta naught, which is a higher energy spin state. I don't know how necessary. Some of this is going deep in the theory. I'm not going to test on this. This says NMR requires a strong magnetic field. That is true. So there's different strengths of magnets out there. The higher the strength of the magnet, the more resolution you're going to get. They're talking about this superconducting material. So yeah, that you have to have a superconducting material, and the temperature is around 4 Kelvin. How do you get that? I don't know why they don't mention this, but you have to use liquid helium. And to cool down the liquid helium, you use liquid nitrogen that pulls heat away. If you run out of liquid helium and you don't maintain this temperature, you quench the instrument and you basically have a useless instrument. Here's a picture of an NMR right here. You do have a radio frequency generator. It says deuterated solvents. The reason why they use deuterated solvents, because if they use one that had a hydrogen signal on it, then it would pick up that signal. What they specified, you can specify the frequency where you don't pick this deuterated signal up. Yeah, you could pick it up if you wanted to, but generally it's not picked up because you're not interested in that deuterated signal. So that's why you're looking at that proton NMR instead of this right here. So it's deuterated, so we're not picking that signal up. What was I going to say about this? There was something in the news yesterday. I read that this could be harmful for you. That's dimethylene chloride. So NMR spectra contain a lot of structural information. You want to look at the number of signals. The signal location can tell you, maybe what kind of functional group you have, signal intensity. You don't have to do this now, but you used to have to hand integrate this stuff like this. But again, a computer does that all for you now. There's a number of signals in a proton NMR. Spectrum indicates a number of different kinds of protons in the compound. Identical protons are chemically equivalent. Such protons fall into the category of being either homotopic or enantiotopic. It says homotopic protons. The molecule has an axis of rotational symmetry that allows one proton to be rotated onto the other without changing the molecule. So if we rotate this, and we're not changing the molecule, again, we're not changing the molecule. If you rotate this 180 degrees, we're not changing the molecule. Then another test for a homotopic proton is to replace the protons one at a time with another atom. They're just replacing it with a D. So if the resulting compounds are identical, then the protons that you replaced are homotopic. Enantiotopic protons, the molecule has a plane of symmetry. If the molecule has a plane of reflection, that makes one proton the mirror image of the other. So replacement test is universal. It will work to identify any equivalents of protons, whether they are homotopic or enantiotopic. The resulting compounds are enantiomers, and the protons that you replace are enantiotopic. You can see we have enantiomers right here. We have that mirror plane. So to determine if protons are equivalent, look for rotational symmetry. If none is found, then look for a plane of symmetry. So this replacement test produces diastereomers right here. These protons are called diastereotropic and not chemically equivalent. So if the protons are neither homotopic nor enantiotopic, then they are not chemically equivalent. Just consider the indicated hydrogens below in 2-butanol. It says these protons cannot be interchanged by rotational symmetry or reflection symmetry. We see they talk about some shortcuts, and we'll get in more into that when we get into our homework. These are chemically equivalent because if you rotate this, they'll be the same thing, but with this alcohol group right here, they're not chemically equivalent. It says the 3 protons on the methyl group. The methyl group, what they're talking about is right here, so they're going to be equivalent. These 4 protons are equivalent too. As recall that cyclohexane chairs have 6 equatorial and 6 axial. So the axial and equatorial protons have different electronic environments. But you're only going to see one signal observed in the proton NMR. And that's because at room temperature, remember, this interconversion occurs rapidly. So that's why, you're seeing just one signal. It says in many NMR solvents, 1% TMS is added as, why do they add this as an internal standard? So then you have a baseline of where, the peak should start off at. So the shift for a proton signal is then calculated as a comparison to the TMS. That's tetramethylsilane. Going to that. I don't see this as most proton signals appear between 0 and 10 ppm. That's probably the highlight of this slide. And it says units for delta are often given as ppm or parts per million, which simply indicates that the signals are reported as a fraction of the operating frequency of the spectrometer. So here's your TMS signal, and all the other signals are based relative to your TMS signal. So this is downfield, and this is upfield. It says shielded protons require a stronger external magnetic field to be excited at the same energy as deshielded protons. So current NMRs analyze samples at a constant field strength over a range of energies. Shielded protons, so here we have shielded protons that have a smaller magnetic force acting on them, so they have a smaller energy gap and absorb lower energy radio waves. So these would be higher energy radio waves, and they indicate that for you right there. Alkane protons generally give signals around 1 to 2 ppm. You can see that. Protons can be shifted downfield when nearby electronegative atoms cause deshielding. So these electronegative atoms are causing deshielding. If we go back to our chart right here, we see that deshielded protons are downfield. And the more we add on there, the more they go downfield. So to predict chemical shifts, start with the standard ppm for the type of proton. And you can use it. There's other tables out there besides table 15.1, but this is the one that the book provides. It says the effect of neighboring functional groups on the chemical shifts. It says the effect on the so you have an oxygen of an alcohol or ether plus 2.5. Oxygen of an ester, plus 3. It says the effect on beta protons is about 1/5 the effect on alpha protons. So you don't have to memorize this. You can use your chart. Let me see something here. So when the electrons in a pi system are subjected to an external magnetic field, they circulate and produce a magnetic field causing diamagnetic anisotropy. And we're talking about, maybe like benzene here, or some type of pi system. This diamagnetic anisotropy means that different regions of the localized space have different magnetic strengths. And here they're showing you some type of phenol group where we see the aromatic protons over here. So the result of a diamagnetic anisotropy effect is similar to deshielding. So remember, deshielding, we're going down this way. More magnetic field means more energy required to spin and flip the protons. So the aromatic protons appear in the region of 7 ppm. So if you see something around here, you see some type of aromatic protons. So we have a pi system right here, 14 aniline. Protons outside the ring appear at 8 ppm. And the protons inside the ring appear at -1 ppm. I don't think they should. I don't think this is -1. This is +1, or around approximately 1. So it is necessary to be familiar with the ppm values of these common types of protons. So, remember the phenyl group, aryl group around 7. You can use this chart if you want to. The more X's we put on there, the more we shift it downfield. Oh, then they talk about integration. Okay. So the integration area under the peak quantifies the relative number of protons. So this might tell you, this might have 2 protons. This might tell you you have 4. I'm just saying, for instance, the computer will do this for you. The computer will calculate the area of each peak representing that area with a step curve. So we see that we get 1, 1.48, 1, and 1.56. So if we doubled it, then we get, 2, 2.96, roughly around 3, 3, 2, and 2, right? So the integrations are relative quantities rather than an absolute count, because we're not going to count, oh, we have 3.12 protons. So the symmetry can also affect the integrations. So we're looking at that last compound right here. So molecular formula must be known in order to know the absolute ratio is actually 4:6 and not 2:3. Here's 2. That's how you get your 4. And then you get your 6 from counting these ones. And if I label these all A's, you get your 6. So this one sees 4 over here. So this is more likely this one. This one, the triplet. So this is probably this one. So multiplicity is a splitting pattern, the number of peaks in a given signal. Sometimes you'll have singlets, doublets, triplets, quartets, quintets, sextets, and septets. It's just a splitting pattern. This is multiplicity results from magnetic effects that protons have on each other. I consider the protons HA and HB. Since the protons align with or against the external magnetic field, there'd be 2 different magnetic environments for HA. So then with this one, there's 3 different environments. And you see it as a triplet. You could just count this as 1, and then you could add this right here, and that's how you could get a triplet too. Now consider a scenario where HA is split by the 3 neighboring, and now we have a quartet. It sees this signal, it sees this signal, and it sees this one. It says table 3 or 15.3 shows how the multiplicity trend continues. You can kind of predict some of these patterns. When there are n number of neighboring protons that are chemically equivalent, there will be the n+1 peaks in the signal. And we kind of saw this right here. We saw 1, and we added n plus 1. So equivalent protons cannot split one another because they resonate together. To split each other, protons must be within a 2 or 3 bond distance. So here they're showing you that splitting is observed here. Splitting is generally not observed between these two because they're just too far apart. So the n plus 1 rule only applies to protons that are all equivalent. The splitting pattern observed for the proton shown below will be more complex than a simple triplet. That's because now we have this alcohol. The degree to which a neighboring proton will couple to its neighbor is called a coupling constant, or a J value. The J value is the distance between the peaks of a splitting pattern measured in units of Hertz. So here we're seeing these two right here. So we're going to get our triplet, and then this is right here is seeing these ones right here. That's how we're getting our quartet. So I'll go ahead and erase that so you can see that. So remember I talked about in the beginning, so the bigger the magnet, the better the resolution. So they're talking about that here. Higher field strength instruments will give better resolution between peaks because the coupling constant is a smaller percentage of the overall frequency available. So here we see a 300 megahertz magnet. Here would be a 60 megahertz. You can see right here with the 60, we're having overlap. Here, resolution means can we see the peaks? And here we see the resolution right here. Because we're able to distinguish between B and C. Sometimes recognizable splitting patterns will stand out in a spectrum. Like here, here you're seeing your quartet. You're seeing your triplet. Triplet and quartet must have the same coupling constant if they're splitting each other. The peak with integration equal to 9 suggests the presence of a tert-butyl. An isolated isopropyl group gives a doublet and a septet. Here they're all equivalent. That's why you're seeing only one signal and you have 9 hydrogens. Here this hydrogen sees these 3 and these 3. So you have your n plus 1. So it's seeing 6 plus 1. That's how you get 7. Here n is 2. 2 would be 1 plus 1. That's how we get 2. We get this right here. And these are equivalent right here. They're the same hydrogens. We see a doublet. But then that represents 6 hydrogens. And how do you know that? Because the computer is going to integrate this for you. And the computer is going to integrate this for you too. And you can see how this intensity is a lot less because it contains less hydrogens. This complex splitting results when a proton has 2 different kinds of neighboring protons, and we see all kinds of different neighboring protons here. And the molecule shown, HB, is split into a quartet by HA and into a triplet by HC. If JAB is much greater than JBC, then the signal will appear as a quartet of triplets. We can see that right here. It's a quartet of triplets. So you have 1, 2, 3, 4. That's what that quartet. And then we have triplet signals. You see 1, 2, 3. A complex splitting results when a proton. Okay, so JBC is much greater than JAB. The signal will appear as a triplet of quartets. We see that here. If JBC is similar to JAB, then several lines may overlap and the signal is called a multiplet. So that's what this is, just a multiplet right here. I said splitting is not observed for some protons. Consider ethanol. We're not seeing the splitting right here. The protons bonded to the carbon split each other. So they're talking about these protons. This one will be, this one, I should have, here, and this one will be right here. But that alcohol group is not going to split. And they know this because they experimentally determined this. So the hydroxyl proton and other liable or exchangeable protons undergo rapid exchange with trace amounts of acid. So such exchange blurs the shielding. So they experimentally determine this, right? And then they have to think about, why does this happen? So, they're giving you this explanation right here. Such exchange blurs the shielding, deshielding effect of the neighboring protons, giving a singlet that is often broadened. So to give you some examples, the 3 molecules below might be difficult to distinguish by infrared spectroscopy or mass spectrometry. But they're easily distinguished proton NMR because they do not have the same number of equivalent protons. So oftentimes you're going to use your MS with NMR, to confirm what you have, or you can use all 3. You could use NMR, FTIR, and mass spectrometry. With a given signal and a proton NMR, they're just giving you a 5-step process. It says calculate the degree of unsaturation. We did that in the homework yesterday. Consider the number of NMR signals and integration. You want to analyze each signal and try to guess. Assemble the fragments and verify the proposed signal. It says, the proton is, the hydrogen 1 is by far the most abundant isotope of hydrogen. Carbon-13 only accounts for about 1.1% of carbon atoms in nature. So as a sensitive receiver coil and/or concentrate NMR sample is needed. you have to have a more concentrated sample is what they're saying for carbon-13 NMR. Says carbon-13 samples are generally decoupled. You'll just generally see them as singles. You won't see these doublets or triplets. So the vast majority of the singles in carbon-13 spectra are singlets. And what do they mean by that? That means you're only going to see one signal. You're not going to see, generally, you're not going to see doublets or triplets. You're just going to see one signal right there as a singlet for carbon-13 NMR. To use the carbon-13 NMR and the proton NMR to elucidate the structure. As compared to proton NMR, carbon-13 atoms require a different frequency of energy to excite. Compared to the standard TMS, carbon-13 NMR signals generally appear between 220 and 0 ppm. So remember, with proton NMR, we're generally looking between 10 to 0. With this carbon-13, I should draw like this. With carbon-13, we're looking between 220 and 0 ppm. So you can see we really extended the range right there. So knowing how symmetry affects the number of carbon-13 signals for these compounds. Here we have 4 different signals because these are equivalent on this side, right? If I call this XA, this should be, XA, B, XB, C. These are all equivalent. Here we see 5 signals, and here we see 3. That's because this is equivalent to this right here. Here's your 1 signal. If I call this one Z, if I call this one Y, so you'll have 3 different signals right there. So like proton signals, chemical shifts for carbon-13 signals are affected by shielding or deshielding. So deshielding means more downfield. And they give you an approximate area to look for different, functional groups. Remember, though, that the carbon-13 are not going to tell you how many hydrogens are attached, though. Since carbon-13 spectra generally give singlets, we talk about that. I've done actual carbon-13 NMR, so I do know about that. And oftentimes what they're not telling you is to get a clearer resolution, they never said this, you want to run more repetitions with the same compound. So the more reps you run, the better the resolution, better the signal gets, and that stuff takes time. So I remember running some samples that would take 10 to 12 hours so I could get a really good clear signal. Sometimes you don't have to do that, It all depends on your sample. This is a different type of NMR. We won't go too much into this. And then they're just showing you that, you know, that MRI uses the same concepts as NMR. And with MRI images, you can see, you know, it gives medical professionals an idea of what's potentially going on. So that's it. We will take a 10-minute break. We'll take a little shorter break today. Well, let's take a 5-minute break. And then we'll be back in 5 minutes and we'll go on with the homework. All right, we are ready to go on with our homework. So let's get to it. Chapter 15, question 1. It says, select the solvents that are commonly used to prepare a sample for proton NMR. Remember, we can use anything that says deuterium. Anything that has deuterium, you're going to select that option, okay? So, you know, if you see deuterium, you're going to select that option. If it has D6, you know, or D, you're going to select these options. So there's 3 options you need to select. Because we're looking for we're looking for an isotope that's not going to interfere. And deuterium is not going to interfere with our proton NMR. For question 2, we can do it on the same slide. It says predict how many different proton NMR signals we'll see. So we have some really good symmetry right here. I'm going to redraw it how I think it should be presented. So we can count, you know, 1, 2, 2, and 3. I could have labeled it A, B, and C, but here's 1, here's your second signal, and here's your third, so you're going to select 3. So for methylpropene, we can even do this on this slide too. What we have. Here's methylpropene. How many different signals do we have? I'm going to call this one A, and all these ones are going to be B. So then you're going to have 2 signals. So question 4, it gives this compound right here. And you see chloride here, they have a methyl group. I'm just going to draw it like that. And then you have a hydrogen here. You got a hydrogen here. It says, you know, the protons, they're identifying these protons right here. They're going to be diastereotropic. Because if you replace this with a D and you redrew it over here, you'd see an enantiomer, so it'd be diastereotropic. Select that option there. Any questions so far? All right, we'll go to 5 then. Question 5 says, analyze the structure to determine which contain enantiotopic protons. So we're looking for enantiotopic protons. We're going to select the one that has OH and Br. So if you have options to select OH and Br, you're going to select those. Okay. So I don't know which options those are for you, but they're B and C for me. So if you see 2 bromines or just 1 hydroxyl, you're not going to select that one. Remember, enantiotopic protons would be, where you would be able, if you replace the H with one H with a D, or one hydrogen with a deuterium, or whatever you want to call it, you should see a enantiomer on the other side, and you do with B and C, because then you have four different constituents coming off. We'll go to question 6. Question 6 is an NMR signal is observed at 151 hertz downfield of a tetramethylsilane. Remember what tetramethylsilane is? Yeah, 4 different methyl groups coming off. On a 135 megahertz instrument, I'm being honest with you, 135 megahertz is a weaker instrument. It says, what is the observed chemical shift in parts per million? You just take 151 divided by 135, now you get 1.12. So you may have different numbers, so make sure your numbers are, if you have 145, you got to take that into account. I said, what is the chemical shift in parts per million if the sample is analyzed at the 300 megahertz instrument? Let me think about that. Let's just say, we increase that 135 megahertz instrument to, if we multiply by that by 3, if I multiply this by 3, I get 405. Like 151 times 3. If you multiply each by these by 3, you're going to get the same answer. It's going to be 1.12 because it's a ratio. So then if we take this 1.12 times 300, which is our new instrument, we get 336. All right, so that's 6. Let's go on to 7. As given the structure that corresponds to the following molecular formula and proton NMR, draw the structure. So they give us the formula. So we just draw it like this. We have our structure. We have 5 carbons and we have 10 hydrogens. Question 8, they give us this compound here. Oh. And they want us to kind of draw the what we're gonna see, and they give us some blanks so we don't have to guess. This one's around 4. This one, I'll just. So these 3 hydrogens right here are going to be alone as a singlet. Then we have these 2, and this will be seen right here as a quartet. Then this will be here. And then obviously then there's only one possibility left. So you'll draw that. All right, so let's go to 9. Gives us the spectrum. It tells us we have, so we have chlorines here, right? We have a hydrogen, we have 3 hydrogens here. And we have to put where we think this might go. This proton right here is going to be way downfield. Around 6 to 5. And then we're going to see these ones right here as they doublet. And we're going to see this closer to 2. That's question 9. Question 10. They give us some chemical shifts. They give us relative integrations. They tell us the multiplicity. We have to draw the structure. So I'll go ahead and do that. And it gives us a molecular formula, so you can kind of guess what might happen on this. We have 5 carbons. And that's what we have then. Sorry about that, I drew this wrong. That's a methyl group right there. So you have 1, 2, 3, 4, 5. Yep, I have 5 now. This is going to be around 2.26. This one will be around 5.87. Around 2. And this one around 1.06. All right, so let's do 11 on this same slide. The bottle is labeled only compound B, C6H12. They give you a chemical formula. It contains a colorless liquid. You've been called in as an expert, and they give you some IR spectra. They give you a proton NMR. And the NMR spectrum shows a typical isopropyl pattern, a septet, and a doublet. So that's what we want to draw. I think they want you to put in the hydrogen, so we'll put them in. That should work. So you should have 11 done now. All right, so let's go on to 12. To identify the unknown compound, they give you C4H6O, give you some proton NMR, give you an IR. The compound liberates a gas when treated with C2H5 MgBr. So we'll draw that. That should help you out with the identification. And I tell you what you have here. All right, so that's 12. So 13, we can do this on the same slide. They have 3 signals here. They tell us we have C4H10O2. We have 3 signals though. So how do we get this? Here's one signal, here's your second signal, and here's your third signal. And just kind of mirror it. All right, so that's 13. Let's go to 14. So for the protons labeled HA and HB in the structure, predict the characteristics of their signals in the proton NMR spectrum, approximate chemical shift, the splitting pattern, and the integration value of their signals. So the approximate chemical shift of HA. So remember, we have a phenyl group here. So that phenyl proton is going to be 7 to 8. This will be 7 to 8. The expecting splitting pattern of HA will be a doublet. And the reason why it's a doublet is because, oh, and I should put the HB here. It's going to be a doublet because it's going to see this and it's right by this, right? So it's not all equivalent. So it's going to be a doublet. This splitting pattern of HB is going to be a triplet because it's going to see this and this. So this is going to be a triplet. The expected integration value of HA. Well, there'll be another HA here. So the integration should be 2. And the integration value for the HB, well, there's only one that looks like HB. So even though we have a triplet here, we're only going to have one hydrogen. So that's 14. Let's go to 15 then. They give us, oh. The approximate shift of HA. So this, we're talking about the hydrogens here. This is going to be around 2. For B, again, we've kind of talked about that already. The expected splitting pattern of HA. This will be a singlet. How many hydrogens? 3. For HB, it will be a doublet. So this will be a doublet here. And you're going to see 2. That's supposed to be an integration, so we see 2 here because this will be equivalent right over here. So that's that one. So we'll do 16 on the same slide. 16 says deduce the structure of the unknowns compound. We give us C10H10O2. It has 1, 2, so two signals. One has 6 hydrogens, the other one has 4 hydrogens. You can see the one with 8.13, this will be a phenyl group. So we're going to have a phenyl group. Here's our 4 hydrogens here. And then we have an oxygen. Here's your oxygen, and here's your methyl group, and here's your 6 hydrogens here. So that's your compound. Any questions so far? All right, so let's go to 17. The C9H10O3 has IR absorptions at 2300 to 3200. Gives us the proton NMR. Consider the proton NMR. It wants us to draw a possible structure for this. We see that we're going to have a phenyl ring. IR spectra seems like we're going to have some type of OH with it. So we're going to have this. Sorry about that. That's going to be a singlet all by itself. There you have multiplets where you have 3 hydrogens and 2. That's 3 hydrogens and 2, and that's going to be your phenyl ring. All right. So let's go to 18. Same type of setup. You know, it wants us to identify what we have. It says we have a molecular mass of 71. So we'll draw this. The IR is strong and broad, so we have that alcohol group. Gives us the proton NMR. that's what we have. '19 is another one that wants us to provide the structure, so we'll do that too on the same slide. With C10H13NO2, we see we have a phenyl group and we have some multiplets above 7. We're going to have a ketone. We do have a nitrogen in there. So we'll draw our phenyl group. You have an ester. And you have your ketone. So let's go to 20. 20 says how many unique carbon-13 NMR signals are here. And we're looking at carbon-13. Think about this. A, B, B, C, C, and D. So that's 4. That's 20. For 21. It says how many, so it has a bunch of different compounds A through D. Oh, this is not writing for some reason. So for this one, our different proton signals. For proton, we're going to have 2. For carbon-13, we're going to have, so that'd be 3. For B, we have this. How many different proton signals we have here? We have, well, you're going to have 4 different proton signals, so this will be 4. I'm going to label the carbon ones with just numbers. So 1, 2, 3, 4, 5. So you have, this is your proton, your carbon-13. Now working over to C. Our different proton signals are here. 1. This will be the same for proton. And then for carbon, so for proton NMR, you have 2. Carbon-13. Let me see. These are equivalent. These are equivalent. So you have 2. D. This. For proton NMR, you're going to have carbon-13. 2. So that's 21. So here's your answers: 2, 3, 4, 5, 2, 2, and 1 and 2. 22. It gives us a formula C7H8, so there's really not too much you can have with this. If you want to know the truth about it, you're going to have all this going on. That gets me 5 hydrogens. And how do you get the other 3? You do that. So that's 22. It gives us a proton NMR and a carbon 13 NMR. It shows us some protons that are de-shielded downfield. So I know I'm going to have a phenyl group. So I'm going to draw that phenyl group right away. With that phenyl group, I'm going to have four different hydrogens on there. So you know that these are all going to be equivalent. We'll have that. Three hydrogens here, 2 there, 1 here, 2 here. That's 23. We can put 24 on the same slide. We'll put it right here. It says consider tert butyl alcohol. And then it wants you to put how many signals you'll have. You'll have 2 singlets, one around 70 to 60, or one around 30 to 20. These are all equivalent. This one's on its own. $25. It gives us C4H6O. Let's draw the structure. We want to first calculate the index of hydrogen deficiency. That way you can see how many double bonds you have. So we have 2 carbons plus 2 minus how many hydrogens we have? We have 6 divided by 2, 4. So that's 8 plus 2 is 10 minus 6 is 4. So we have the hydrogen inefficiency index of 2. So that's our unsaturation number. So we're probably going to have 2 double bonds in here somewhere. That's our index of hydrogen deficiency. So here's your 1 hydrogen, here's your 3 hydrogens, and here's your 2 hydrogens over here. So that makes sense. So it's important to calculate this, otherwise we don't know how many, double bonds we're working with, because we have an unsaturated compound here. So we have then 26, our last question. It says, consider the carbon-13 NMR and the expected chemical shifts of common functional groups. The given chemical shift ranges are approximate. What is the expected chemical shift in aliphatic ketone? Aliphatic ketones occur around 180 to 210. That's just something that you have to look up in a chart. So are there any questions? We're done with the homework. We completely finished chapter 15 today. All right, seeing no questions, you are free to go. Have a great weekend, and we will start chapter 16 on Monday.